Hey everyone, so if you've ever run a Spark job, waited for it to finish, then run another action, and just wondered, why is the entire thing starting over from scratch? Well, then you have run smack into the exact problem we're going to tackle today. We're diving into one of Spark's most powerful optimization tools, persistence. Let's get right into it.
Okay, so first things first, let's talk about a super common snag that trips up a lot of developers when they're new to Spark. It's that classic, why is this so slow moment that actually tells you something really fundamental about how Spark works under the hood. So picture this, you've loaded your data, you've applied all these transformations to create the perfect RDD. You run a count action, and great, it works. But then you go to run a first action, and you see your whole cluster just light up again, redoing everything from the very beginning. What is going on? Well, the answer is all about a core Spark concept. See, Spark has this thing called lazy evaluation. And what that means is when you tell it to do a transformation on an RDD, like a filter or a map, Spark doesn't actually do it right away. Nope. It just jots it down, building up this kind of recipe of instructions. We call that the lineage graph. It's only when you call an action, something that needs a final result, like a count, that Spark finally looks at that recipe and says, okay, time to get to work. And this right here shows you exactly why that can be so inefficient. By default, every single time you run an action, Spark follows that recipe from step 1. So when you call count at all, it reads the data, does the transformations, gets the number. But when you then call first, it does it all over again from scratch. For any kind of complex job, this is just a massive waste of time and resources.
Now, this whole recomputation thing, it's not a bug, believe it or not. It's actually a feature. It's designed for these huge data sets where you might not want to waste memory storing intermediate results. But what if you do want to store them? Well, that brings us to the solution, persistence.
Which leads to the obvious next question, right? If Spark is redoing all this work, there has to be a way to just tell it, hey, I'm going to need this RDD again in a minute, so please just hang on to it. And boom, there's our answer. Spark gives you two really simple methods, .persist and .cache, to do exactly that. When you call one of these on an RDD, you're basically flagging it for persistence. So the first time an action is called, Spark computes it like normal, but it also saves the result so it's ready to go for next time. So what's the deal with these two? Think of .cache as the easy button. It's just a shortcut for the most common thing you want to do. Stick the RDD in memory. On the other hand, .persist is the more powerful tool. It gives you fine-grained control over how and where you want to store that RDD. And this is where it gets really interesting. With .persist, you're not just stuck with storing data in memory. Spark actually gives you a whole range of options, and each one comes with its own set of trade-offs. Exactly. Where can we actually put this data? And how is that choice going to affect performance or our memory usage, or even the CPU load on our cluster? Okay, let's break down the big ones. Memory only is the default for .caching, and it's the fastest because it stores ready-to-use Java objects right in memory. But it's also the most memory-hungry. If you need to save some space, memory only stores the data serialized, so it's more compact. The catch? You pay a CPU price to deserialize it every time you need it. And if your RDD is just way too big for memory, you can use disk only, or my personal favorite, memory and disk, which is a great balance. It tries to keep data in memory, but spills over to disk if it runs out of room. The bottom line is, you gotta pick the level that best matches your data size and your performance needs. Now, you might be worried, what happens if I try to cache more data than I have memory? Well, the good news is, your job won't just crash and burn. Spark has this built-in safety net. It uses what's called a least recently used, or LRU policy. Basically, it'll automatically kick out the oldest, least used data to make room for the new stuff. Sure, you might have to recompute those old partitions later, but your application will keep on chugging.
So we've talked about performance, but what about reliability? I mean, this is a distributed system, right? Nodes fail. It happens. What happens to our carefully persisted data when it does? And this is a super critical question for any real-world application. If you've spent all this time and energy computing and caching a massive RDD, the absolute last thing you want is for it to just disappear because one machine in your cluster decided to take a nap. And the answer, thankfully, is a resounding no. Persisted data in Spark is fault-tolerant. This is honestly one of the most powerful features of the whole architecture.
So how does that work? Well, it all comes back to that same concept we started with, the lineage graph.
Because Spark always remembers that recipe for an RDD. If a piece of your persisted data gets lost, Spark can just pull out that recipe and rebuild it on another machine, no problem. So the lineage graph isn't just for lazy evaluation, it's the fundamental blueprint for fault tolerance. It guarantees that no data is ever truly lost, because the instructions to recreate it from scratch are always preserved. This is what makes Spark so incredibly resilient.
All right, let's do a quick rundown. First, Spark's lazy evaluation means RDDs get recomputed with every action by default. To stop that, you got to use .persist or .cache on any RDD you plan to use more than once. When you do, make sure you choose a storage level that balances speed against your available memory and CPU. And finally, remember that the whole system is fault tolerant, all thanks to the power of that lineage graph. Getting a handle on these concepts is a total game changer for writing professional-grade Spark code. If this breakdown was helpful, please be sure to like, share, and subscribe for more content just like this.
And that brings us to the end. So I'll leave you with this question. The next time you're writing a Spark app, take a second to think about your data flow. Look for those RDDs that are expensive to compute and get used over and over again. Those are your prime candidates for persistence, and caching them is your ticket to a much faster and more efficient job.